everybody. Today we're going to focus on talking about not only vectors, but more importantly today we're going to focus on complex numbers that can be represented as vectors. So as a little bell ringer warm-up today, what we're going to do first is take a moment to answer 1, 2, and 3 by simplifying the following complex expressions. Now, to double check your work, one thing I like to think about when I'm simplifying complex expressions is think of that I like a traditional variable when it comes to simplifying expressions, and when you're combining kind of those like terms and making sure you're distributing when necessary to combine. So for the first one, you should have had 4i as your answer. Oops, 4i. There we go. The next one, when you distribute and combine, you should have had -2 minus 3i. And then last but not least, 12 times 3 is 36. I times I is I squared, but that's better known as -1. So -1 times 36 is -36. Okay. Now, again, as I mentioned before, our goal today is to start talking about the complex numbers being represented as vectors. We're going to skip over a lot of these notes, so do not be alarmed that we're starting on page 454 in the notes, but we're going to skip over a lot. We're not going to do all 9 pages of these notes. Now, when we talk about complex numbers being represented, first and foremost, notice that the form that these complex numbers are in is a plus bi. A is going to represent a number, B is going to represent a number, and the Z is representing our complex plane. So if we look down below, another important thing to notice, the y-axis here is our imaginary axis. The x-axis is now known as the real axis when we're talking about a complex plane. So notice here, when we graph these particular pieces here, we're graphing these on the plane. Z equals 1, 1 is going to be representing the A value, and we're going to go 1 unit to the right here on our plane. So there's A. Now B, let me change color on this, right, is 2i. So that's the B value is 2, and the I we're representing then again on our imaginary plane. So there's B. Now, C incorporates both an A value and a B value. So we are going to treat this one, if we again change colors for C, we're going 2 units to the right and 1 unit down if we look over here at C. So 2 units to the right, 1 unit down, here would represent the complex vector for C. And then last but not least, for example D, we went 3 left on the real and then 2 down with the I there. So 3 to the left, 2 down, our vector would be represented right there for D. Okay, so from there, scroll down here, we can also add and subtract complex numbers both geometrically and symbolically. Now, when it comes to adding vectors, just like we have to do in the bell ringer, we're going to be combining those A components and we're going to combine those B components. So algebraically here, if we look at this symbolically, adding these two together, -2 plus 4i, and then plus the vector 2 here, 3 minus I, we're going to combine -2 and 3, we're going to get +1. Oops, take off my highlighter setting here. We're going to get +1, and then the 4 minus the 1 with the i's, we get plus 3i. So there symbolically is our answer for that addition for A. Now, if we were to talk about this, graphically, geometrically, basically what they're saying is that initial vector Z1, we went 2 to the left, 4 up, so there's Z1, and then from there we went 3 to the 1, 2 right, down 1, so here's Z2. So that resultant vector is, again, this 1 plus 3i. That's the representation then geometrically as well, okay? Now for part B, we're subtracting the 2. So again, be careful to distribute the negative through for Z2. Our answer here, then we would have -2 minus 3, so that's -5. so really we're adding, we get positive 5i. And again, if we were to graph this original here, again, our resultant vector then ends up being this negative 5 plus 5i. So 5 to the left, 5 up. Again, you will see that resultant vector. Now from here, when we talk about adding and subtracting, then again, kind of to summarize this, you would add your real parts and you would add the imaginary parts. And then when we talk about subtraction, again, you're going to subtract real parts and then subtract your imaginary parts. Abbreviate here. Okay. And again, very similar to the bell ringer. Again, I like to think kind of a combining like term situation here in order to combine these. But take a moment, pause your video on your own, and just answer A, B, C, and D on your own. Now to continue on with this lesson, some of the big things that we need to talk about today then are how do we find the absolute value or modulus, and how do we find the argument. Now, when we talk about absolute value, and kind of to compare it back to what we've been talking about before, the absolute value of a complex number works basically the same way the magnitude of a vector works. So notice these forms here with the z plus bi here. And when we talk about the absolute value, it's going to talk about, again, finding for us kind of this distance value, if you will. So in order to find this, and this is something you definitely would make sure you write down, to find that absolute value of z, or you might see it represented like this absolute value of that complex number, it's taking the square root of a squared plus b squared. So again, very, very similar to that magnitude that we talked about before. The other important piece here that we're going to talk about is the argument. Oops, scroll down on this. Is the argument of a complex number. So if you flip the page to page 456, the argument, just like the absolute value works like the magnitude, the argument is going to work like the direction of our vector. So again, the argument here is going to be represented like this. You're going to see ARG of your complex number here, and that again is going to work like the direction. So in order to find this, what you're going to have to do is, in order to find that reference angle, you would take tan inverse of b over a. Now, a reminder, location matters. So again, what quadrant are you in? Because your angle measure here, your argument needs to match, okay? So make sure you take into consideration, if you think back to here, you're going to have a theta measure, 180 minus theta, 180 plus theta, and 360 minus theta. To kind of keep that in mind again. And remember your axes then, 0, 90, 180, 270, if it's on an axis for your arguments. Okay. So this next part then kind of asks us to determine the absolute value and the argument of each of these values below. Now, one thing I definitely like to do with this is always sketch myself a picture, because especially if this ends up on an axis, it's much easier to come up with your argument if you know you're on an axis. So for this first one, for instance, if we are at z equals 1, well, that means that's a positive a value of 1, which means that you just need to go, oops, 1 unit here to the right. So this is kind of your picture, if you will, on this. There would be your complex vector. Well, what this means for our value of the absolute value, so we would represent that here. The square root of 1 squared plus 0 squared is just 1. That's length of our vector. And then without even taking tan inverse, if we went to the right, our argument here, and if we're on that positive x-axis, the argument of z is just going to be 0 degrees because we're on the axis. Right? So that's why I like drawing the picture kind of first in my brain, just to see where things are at. And that's going to be a similar tactic that's going to help us with example B. Because what we can do here then is if we're at 2y, we're at positive 2 units up on the imaginary axis, which means this time our absolute value is going to be the square root of 0 squared plus 2 squared, which is just 2. And the argument of z this time, again, we're going pointing straight up, that's going to be at 90 degrees. Now, the next couple examples get a little bit trickier because we have both an A and a B component. So we are 2 units to the right, 1 unit down. So 2 to the right and 1 down. It's kind of the approximate picture we have going there. And we're going to do a little bit more work this time because our absolute value this time is going to be the square root of 2 squared plus negative 1 squared, aka the square root of 5, or the approximate value of that is about 2.2, depending on how you're writing your answer. And then in order to get our argument this time, a reminder to get your argument, you need to take the inverse of b over a for tangent. Okay, so if we look here, tan inverse of negative 1 over 2, you have negative 26.6-ish degrees. Now, negative 26.6 would be an acceptable answer because that is in quadrant 4. All right, another acceptable answer is if we add 360 degrees to this to get that value between 0 and 360. You would also see 333.4 as an acceptable answer here. So negative 26.6 degrees or the 333.4 degrees works as well. Okay. And last but not least, I'm going to drop this last one down for D to the right here just because we ran out of room. But if you're at negative 3, negative 2, you're 3 to the left on the real axis, 2 down on the imaginary axis. So it's almost like quadrant 3. So we're going to keep that in mind for our argument later. Now, the absolute value, again, is the square root of negative 3 squared plus negative 2 squared. So we end up with the square root of 13, or if you are approximating that, about 3.6, depending on how you're writing your answer. And then again, for the argument, you're taking tan inverse here. So b over a, tan inverse this time, we are negative 2 over negative 3, b over a. We get 33.7. Now, a reminder, double check what quadrant you're in because 33.7 is quadrant 1. We're in quadrant 3. So we're going to need to make sure we add 180 degrees to that so that we end up with the appropriate value of 213.7. So 213.7 degrees. Now, talking about this just quickly as well when we kind of move around the complex idea with I here. Remember, 1 times I is just I. 1 times I is I squared, better known as negative 1. And then I to the third we talked about is negative I. Okay, so as we graph this around the circle, the first value here of 1 is on our positive real axis. And if we start moving around the circle here, this would be the value of A. And then we would have the value of B. Just move it down a little bit. Oops. There's B. And then C would be represented by moving this going down here to negative I, aka negative 1 on our axis here. Okay. And that would move around here as well, because just kind of continuing on with this idea, when we get down to I to the fourth, we know that that is back to being equal to 1. And again, you're just basically essentially moving around clockwise is what they're trying to get you at around these axes, that they just kind of keep repeating themselves around.